Section 1.4 is kind of the building blocks of what we're going to be doing for the next couple of weeks. Super duper important. The first few times you do this, maybe the first several times, it's going to feel like it's really tricky. I promise a month from now, you're going to be like, why was that so hard for me? Okay? Super calculator dependent kind of stuff. Also super verbal stuff. So we're going to start with the verbal part, which is what makes a model. There are 4 pieces to every single model that you will create. Always. If you miss one of those pieces, you miss points. You miss them on your homework, miss them on the tests. Always have these 4 pieces. First, you have an equation with a name. So you could say that's 2 pieces in one. A name, right? Like f of x equals, g of x equals, k of x equals, and an equation. Secondly, you have a description for the output with units. You have to tell me what in the world you're finding when things come out of this equation. And how is it being measured? Third, you have a description for the input with units. If I give you, a year, how are you going to put it in there? Are you going to put it in there as 2000, 2000 like the year 2000? Or are you going to put it in there as 10 because it's being measured since 1990? You need to know. And the last piece is an interval for the input data when possible. And I will say it is not always possible to give that input interval. But most of the time when you're creating models, you'll have it. So you're going to say that your data goes from, the data that you're representing by this function is from, 2010 to 2012. Right? Or whatever it is. It's from January to March. Okay? Specifically in this section, we are working with linear models. Linear models, otherwise known as lines, you've typically seen the equation y equals mx plus b. In your notes it says ax plus b, and the reason it does is because your calculator is going to say ax plus b in a minute. Okay? A and b are constants, that means they're numbers. As you probably remember, a is the slope, b is the y value, or is the y-intercept. And generally, slope, which is known as a rate of change, is found in a couple of different ways, more than this, but these are a couple of them. F of b minus f of a over b minus a. y2 minus y1 over x2 minus x1. And the first example that you'll see is already giving you the model. Okay, so this is a model. I'd like to identify with you that it meets all my criterion so you can start recognizing when things are missing, hopefully in your own work before you submit them. First, it has a name, c of x. Second, it has an equation, 0.3x plus 5. Next, it has the output units, it's dollars. Then it has the input units, where x is the number of years since 2010. This one does not happen to have the input data interval. I mentioned before, sometimes it won't be included. It's better when it is, because it doesn't tell you how accurate your information is going to be based on what you choose. For example, if you choose to enter something about the year 2012, it might be pretty accurate. But if you pick to enter something about the year 2050, it might not. That's really far away from 2010, but we don't really know how far away we can sort of get away with, right? Because they didn't give us that input interval. First, what is the slope of the line defined by this equation? 0.3. That's my slope. All right, so here's the slope right there. The second question says, to write the rate of change, this phrase rate of change means slope. Okay? Write the slope of the function in a sentence of interpretation. We've been doing some kind of interpretations for me already. Back in section 1, we looked at some of that already. And a lot of it's actually embedded inside of the question itself. Right? You should go back to the question itself. It almost gives you half of what you need without you really trying too hard. What in the world does this actually talking about? Well, it's talking about the cost of renting a newly released movie, right? In particular, it's talking about the fact that the cost changes over time, just like all costs do, right? They do. So if I take a look at this sentence could look something like this. The cost of a movie is increasing. How do I know it's increasing? Yeah, but sometimes costs will decrease. If you looked at the cost of your cell phones or the cost of a specific type of cell phone over time, they'll go down. The slope tells you. What about the slope tells me that? It's positive. So from a very concrete way, the equation itself tells you, not from the context itself on this one. It's the equation. So this equation gives you a slope that's positive. Well, positive means something's increasing, right? So if I were to graph this function, it would be going uphill like this. It's a slope of positive 0.3. So it's increasing 30 cents. Please don't write that I did $0.3. That's what I just did. You can write that or you can write 30 cents. Don't mix them up. The Sonic right now over on Harrison tells me that I can get a 0.99 cent large drink. Does anybody know what's wrong with that? I didn't write it right. I didn't write it wrong. I wrote it right. This is what their sign says. This is what their sign says I can get. It's less than a penny. I really should try it. Yeah, they mixed it up, right? It should have been, I can't even write it wrong by accident. I had to write it wrong on purpose. This is what it should have said, right? It's 99 cents. It looks like this. Okay. So now you know one of my pet peeves. So make sure that this actually says 30 cents or $0.3, right? So $0.3 per year. So where did I get the per year? Well, I got the per year because slope is y's over x's, right? Well, the output was dollars. The input is numbers of years because it said years after 2010. So that's where the per year came from. It's dollars per year. When a movie is released, is newly released. Okay, so does it have to be word for word? Well, no, but there are pieces that if they're left out constitute something being taken off because you haven't quite got all that there. For instance, that per year part I just mentioned, that has to be there. How is it increasing 30 cents? Well, 30 cents every year, right? I need to know that information. What's increasing? I can't just say the cost. The cost of what? I mean, your description may be not quite as thorough as what I've written down, but it needs to talk about the cost of a movie, at the very least, right? Those kinds of things.
So in this example, the name of the equation is C of X.
It is.
And then the description for the output is 0.3x.
No, that's the equation. The description for the output is dollars.
Dollars is the description.
Yep, the dollars is the description of the output, and then the number of years since 2010 is the description of the input. Okay, one more part to this problem. We've done this idea of evaluation back in sections 1 or 2, maybe both of them. but we haven't done a whole lot of the interpretation for what it means with context. So this says evaluate and give a sentence for f of 0. That should say c of 0, my apologies, c of 0. Well, it means that I'm going to put a 0 everywhere I have an x. And if I do that, please don't grab your calculator, what would you get? 5, right? You just get 5. What in the world does that mean with this problem? What does the 0 mean? What does the 5 mean?
That just means that it's 2010 movies are $5.
Right. The 0 means I'm in year 2010 because it says X years since 2010 and my X is 0. So it actually means that in 2010, and the $5, the output is the cost of the movie, right? The newly released movie. Costs $5. Does that make sense? Okay. So that's sort of taking an equation and its model all in its form to start with, and then sort of analyzing some details about it. The next question that we're given has us actually create the equation. But it's not creating it from a table. We'll get there in a moment. But it is creating it from some data. So here's my data. In 1999, 28% of births were to unmarried women. In 1995, 32% of births were to unmarried women. Write a linear model for the given rate of change and initial output. So if I'm going to have a linear model, that model looks like AX plus B for the equation part, right? In particular, I need a value for A and a value for B. So B would be like the starting value. So if I were considering both of these particular data points, which one would you think makes sense to be the starting value? Yes, it's going to highlight where it was. Yeah, probably, because it's the earlier year, right? It comes first. So kind of would make sense, I think, for my B value to be 32. What about A? What does A represent in a linear model? The slope. So A, which is my slope, is found the same way we would find slope in an algebra class, right? So one of the ways is y2 minus y1 over x2 minus x1. If you'd like, we can use that interpretation. What is x and what is y in this context? Because it's not been like identified for us yet.
So are the X values going to be 1995, 1999?
These are my years, and these are my percent of births, or percentage of women, or whatever it was. Okay? Pretty much guarantee you that if time is one of your variables, it's x. Almost without fail. Okay? So my second y value here would have been 28. The first one would have been 32. My second x value would have been 1999. And my first y value would have been 1995. So my top ends up being -4/5. We're using decimals, like that's what this is gonna do. What did I do? Oh, it is over 4. I have a typo on a problem somewhere. Okay. Yep. Oh, that's why. My problem was different when I created the notes originally. Okay, so this is -1, right? Okay, so my slope's -1. So it's great. I have a slope. I have a y value, intercept. So far, I know that I have -1x plus 32. That is far from complete when it comes to models. So I'm going to flip back real quick to remind us everything I'm supposed to be including. All we have is the equation. We don't even have a name yet. At least I don't on my screen. Yep, it can be, but mine's not there yet. So over here, I agree. That sounds like a good place to start. We need a name. F of x is as good as anything. If you like something better, you can. But f of x will work. Now I have a name and I have an equation. That was all one part. What was the second thing it said that I should have? Output, including the units. What is the output of this function? Yep, it's the percent of births to unmarried women. We're getting there. Now we've got the name, the equation, the output units. What's next? Input units, yeah. So what's the input units on this one? It is the years. So this is where things get a little dicey and people tend to forget things. They like to say something like this, X is years. That doesn't really fly because right now X is being determined by a year with a specific starting point. What was our starting point year here? 1995. That has to be part of my description. So one way to say that is X years after 1995. You can say where X is the number of years since 1995. After and since are probably your best descriptive words. But somehow you have to understand that when I look at this number 32 as a y-intercept, it's representing the year 1995's percentage.
So because our equation stops at 1999.
Yep.
Could we just put to represent the output value or the input? Couldn't we just put between 95 and 99?
Yes, and you can do it two different ways. So you can either do that in words, like you can write out in words like where it sounded like you were suggesting between the years 1995 and 1999. That's fine. Another way is to write it in an interval notation, 0 less than or equal to x less than or equal to 4. The reason I'm getting 0 and 4 is because 0 was the year 1995, so 1999 would be 4 years later. So you can do it as an interval like that. You'll see your book do a lot of intervals that way. That's a really common way. But there are going to be some times too where they'll use verbal descriptions, and either one works just fine inside of your model context, okay? Okay, any question about the creation of that model and all the pieces? All right, so I mentioned before that knowing where things are sort of, where your inputs are sort of valid is really important. And they're really important from the perspective of where your model gives you accurate results. Interpolation is using a model to predict when the input that you're trying to put in is between the interval. So like mine just a moment ago was from 0 to 4. So if I used the x value of 3, that'd be in between 0 and 4. It'd be interpolation because it's in between. If you're wanting to use your model to predict something outside of the interval, right? Something afterwards, something in the future, right? So like, I've been tracking COVID stuff since April 1st because I'm a math person and I wanted real life data, and you're going to see some of it because there's incorporated, embedded in our questions later on. But if I were using the data from March to predict what was happening in June, I would have been wrong, right? Because it changed. And so you have to be careful with predictions. But if I used the data from the last week to predict the next week, well, it probably would be pretty close because it's not that far out. So the idea of extrapolation is using the data to predict something outside of the interval. So even over here, if I used x equal 5, it'd probably be pretty close, but it's still outside of the interval. It would still be considered extrapolation. And I may or may not actually be that correct because I've gone outside the interval. So we're going to use this model we created here. In fact, I'm going to move it over to my next slide so that we have it. Yeah, just a second. I was trying to paste this equation. It's going to be on top of stuff. Let me make it smaller. All right, it's tiny, but at least it's there. This slide? Mm-hmm. Yeah. So we're going to use that equation to do some predicting. Okay, so on part A, here it says use this previous model to predict what happens for the percent of birth to unmarried women in 1998. So if I'm considering the year 1998, what is my input value that I'm going to use? 3. So I'm going to write f of 3 equals. If you want to actually write it out, you can. If you just want to find the output using your value in your calculator or your functions of your calculator, that would be fine. But I have negative 1 times 3 plus 32, and what would that give me? 29. 29 what? Percent. So at the very least, you need percent on there. If you want to be more descriptive and you say percent of births to unmarried women, that's great. But your minimum that you need right there is 29% to answer the question. Not 29, 29%. What about the year 2005? What would I use if I were doing the year 2005? It would be 10. Because I'm doing years after 1995, that's 10 years later. So I'd have negative 1 times 10. Again, either write or don't write this part. It doesn't matter, that in-between part. What would that percent be? 22%. Which one of those is more likely to be correct?
The 29.
The 29. Why?
Because it's inside the data value.
It's inside the data values. Now, could the 22% be correct? It could, but it's less likely than the other one. And we're going to label each of these as either interpolation or extrapolation. So what about the year 1998? Is that interpolation or extrapolation? Yeah, it's interpolation. And how about the year 2005? Extrapolation. All right. So I'm going to push pause on this right here, and we will pick back up with this part of it, because I would like for you to guys have the chance to start working some problems. That's my goal for the practice problems in class anyway. You will see, if you haven't already printed these out, you want to. The next page in your notes is actually an Excel spreadsheet with lots and lots of steps. Okay? This is how to use your calculator to do regression. You will want this list with you when you come to class next time, without a doubt. Okay? Okay? So for Thursday, 1.3 and 1.3 alone will be due. All right? But I can guarantee that 1.4 and 1.5 will be due the following class period, so you'll have 2 sections over the weekend. Okay?